Hello, everybody. My name is Uberto, and we'll talk about a topic which is very close to my heart. Is something that I'm really passionate about. So I hope you will enjoy. And in case at the end there will be some material if you are interested to discuss further. So let's start with the definition of legacy code. This talk will be mostly about legacy code. So there is one word in our industry, at least in UK it's very common, I'm not sure in other countries, but it's the idea of a brownfield development, which is you have to work on someone else's code and old code. And the brownfields came from the industry, I mean the builder world, that means some site that may, with all the structure that may have to be destroyed and rebuilt again. And of course, the opposite of a brownfield development is the greenfield development, where everybody wants to be, where there are just a law of nice green laws and so smooth hills, and you can do whatever you want. So what is the normal perception about brownfield development? And yeah, everybody mostly hate it. And it's something that, okay, you have to do to feed the family, but don't ask me to love it. And but when I was in Japan, one day I came on this kind of pottery, which is, well, it's not a kind of pottery, but is you find in the pottery museum at this kintsugi, which are this pottery with a kind of a gold fix. And at the beginning, when I saw the first time, I was thinking, I don't know, maybe it's a kind of decoration or whatever. But actually, it's not a decoration. It's been something that has been invented in Japan because some, I don't know, emperor, some nice guy anyway, with a nice pottery, broke the pottery and say, oh, come on, this was a very precious Chinese pottery. What the heck to do? Okay, let's go back to the Chinese to fix. And the Chinese fix was very, very ugly. And the emperor said, no, that's really not doing it. We needed to find a nice way to fix all the stuff. And this is Japanese art, basically to fix a broken pot using gold. In the past, it was real gold. And the point is that at the end, the fixed pottery is better than the original. It's kind of more valuable, more experience, and it gives a better, it's kind of more valuable object. And that kind of took me to think a bit about, okay, so we have this, this is kind of the magenta line is the normal legacy code, where we have every new feature will require more and more time and money and resources to be done. And the blue one is a kind of a mythological fixed cost diagram with emergent design, where everything is really fantastic and we are in a kind of a great world. Our code is really, really nice. And so we have a kind of fixed cost for a feature. So even after years, we can add a new feature more or less in the same time, in the same cost that at the beginning of the project. So what I'm thinking is, okay, maybe, just maybe, we can switch from one kind of the other without restarting from zero. But okay, let's see why people really hate legacy code first. Legacy system in general could be, most of this talk actually, apart from the technical side at the end, will be valid for general system, not only software. But So we have, this is, we found a squirrel family inside our production servers. And basically, they are the only one that know how to work. Which is more or less a bit less funny, but what's happening in all big organizations. There are some piece of code that really nobody want to look at. And they are kind of becoming very expensive to run and maintain. And sometimes it's expensive not much in money, but in risk, because if this goes down, it could really take a long time because nobody have to know. So this is one problem of a legacy. Another problem of legacy, the technical debt. Maybe you know about the technical debt. Idea is that you can write a great code that will be no debt, or you have to write kind of crappy code that probably will require you in the future to fix it again. So it's kind of, you can go it away now, but it will be a debt that you have to pay someone in the future. But what's happening if the debt goes up and up and up? At some point, you really have a flow closure. I mean, you cannot send the debt anymore. And this is kind of the feeling with the legacy system. And this is a kind of a funny description of what maybe the legacy system was not such a bad idea in the beginning, but nobody really talk very well at the beginning, and they just keep adding load and load to the poor architecture. And at the end, it's kind of risky. Or there could be some kind of technical solution which are not so smart as they seems at the beginning. And I mean, I don't know how they took this picture. I hope it's a fake, because otherwise I will probably not be in that pool. But sometimes working in a legacy system, you got assigned to a project, and then when you realize the project, you are feeling like being in that pool. Say, okay, I want to go out. Please let me change the project very quickly. And then there is another problem that every time something goes bad, then tend to go bad and bad again because of the so-called law of broken windows. So I don't know if you don't know, but the idea is that you have a nice house, nobody's living, but it's still okay. Then someone broke the windows. And it's not a big deal, just a broken windows. But when other people say that the one window is broken, they start, okay, nobody cares, so I can break the others. And then very quickly, all the windows got broken. And it's more or less in the same in the code. I mean, until the code is kind of a nice code, I mean, maybe okay, but then someone commits some very bad stuff that just make the job done. Then you have to work again. You see that crappy code and say, well, if you wrote this crappy code, my fix doesn't have to be better than this. And so crappy goes on and on. And then, the continuous status management. I mean, I saw projects where basically every single week there was a big emergency, calling people in the night, scanning to the top guys and stuff. And that was completely avoidable. It was not a especially complex project. It was just the very bad state where it was. And at the end, maybe you wanted to retire. You say, okay, let's forget about. Let's remove this from all the system because we have the new one. But we really don't know who is using it. Because there are so many possible connections, and maybe someone wanted to use this once in a month, once in a year, and it's very critical. So who knows? Who is going to take the decision to switch off? Maybe just left it. So this is more or less the usual. I mean, this was the problem, and then let's see what is the usual solution. But actually, before going that, does someone of you work with the legacy system? Okay, just the good public. And how many of you loves to work with the legacy system? Okay, that's good stuff. Okay, we have the legacy system. So what do we want to do? The usual solution. forget it. Let's write again. And manager loves this solution because means budget. They can make a kind of impact. They can make a very nice slide. They can help his career. And developers loves it because, of course, they can put any kind of hyped framework library that they just read about and they really, really wanted to share, to use and put in their CV. So yeah, everybody's very, very happy. So, shiny. But it's really better because it's not that sometimes some technology are not really, just because you can do something doesn't really mean that you have to do something just because it's new. Before this, there was a very good talk about Apache Spark, which is a fantastic tool that we are using in my job. But since we are using the job, we are also using for some stuff that really, really didn't make any sense to use Apache Spark, just because we could have done it with a simple, but much simpler solution. But it's new and people want to use it. And then what's happened? Okay, let's say we want to do the new stuff, and we are rewriting. So why not adding just a feature or two? Who will notice? Why not? That will be better in the slide. So it's just saying that you wanted to rewrite. A lot of people came to you and say, just you are rewriting. There is this little list, and then when you start rewriting. You can, it's especially at the beginning, you rewrite something and you put, okay, this is a temporary solution, but don't worry, let's just put it for a moment. But then someone forgot it about, and then we have to work, and then, it's not an error that the new rewrite left completely unfinished. And I also work in a project where the new rewrite was left unfinished because it was more or less at half of the development cycle. It was completely clear that it wasn't going to meet the requirements. So they started a new requirement. And also that one, after a couple of years, left unfinished. So they are still using the original system that was 6 years ago, and nobody is fixing. And the last time that I heard that they were starting a completely new system. And this is a kind of a stuck in the middle risk. So, okay, you are betting everything on the new system, and what if the new system is not delivering, and the old one is still going worse because nobody is knowing about? Maybe you find the people who work on that, or maybe the people left, So there is a lot of actually hidden cost in rewrite. Costs which are not really easily accepted when we talk about rewrite. Everybody wanted to say, nah, let's rewrite, so let's forget about it. One typical thing is that since you were able to work to write in the first place, you kind of think that it's easy because you have a kind of success bias. So it works. So, those stupid guys who wrote this crappy code were able to do so. We will be much better. So it's not it. But there is a lot of knowledge in the current code, and the code can be crappy, but there's a lot of knowledge condensed in it, and rediscovering all this knowledge can be very costly. And then also the data migration at the end. Data migration is really a nightmare for any kind of a project, but when you do a big rewrite, it can be really, really something that can kill the project. If it's not possible to migrate the actual data, you have to consider to leave the project because you cannot go. So this talk will be about a different approach. Let's change our point of view. Barnes Torstrup, which is quite famous guy, I think, have this very nice quote. Legacy code often differ from a suggested alternative by actually working and scaling. And let's think about. Let's start thinking about how is it so bad, the code, or just that we like just to complain about? And yeah, the founder of Boy Scouts. So he said, you have always to leave the world a better place. What I mean here is that sometimes the problem with the legacy code is, maybe not sometimes, maybe all the times, the problem with the legacy, what really makes very frustrating working with the legacy code is not much that the code is terrible, but the fact that you cannot change it. So being in a bad environment is bad enough, but being in a bad environment and not to be able to change is really, really frustrating. But if you have that power, if you can change, then the bad environment became a kind of challenge, and you can have a kind of a Boy Scout mentality. But to find a way out of the mess, we needed to find a root. And the idea of this talk is that you can basically improve the current legacy code, legacy system, without having to do a big rewrite. But to do that, you needed to find a root, to plan a root, something not that just happened. You really need to study about. And you have to plan for some milestones. And you have to make sure that those milestones can deliver some value and they can be stable in itself. So it cannot be something that you really have to do everything to make it work, but something like, the Boy Scout, that you can do something, improve, and then maybe next year do another step. And there must be solved one problem, because you can do something worse, but we really wanted to deliver some value to the of course, there is a catch, and the catch is that it's not easy, and it's not straight. Apparently, on the paper, a total rewrite usually is faster, so you can say, okay, we can rewrite this in 6 months, 1 year, 2 years. If we do one step by step, probably it took like 2 years. But the problem is that, in the worst case scenario, but you are really risking a lot, you are betting a lot on that. Instead, if you choose the safe route, that maybe not the fastest route, can be a bit convoluted, but at the end, you really lower the risk. So just as an example, something that someone will probably think about, we need a new big rewrite. So we have a client-server application, monolithic, using Oracle, written in C#, and we wanted to switch something like HTML5 with the REST API that works on Cassandra. How you can do that? You cannot do that, so let's do a rewrite. But it's not really true. What you can do is something like, for example, we can, one solution, we can concentrate on the front end, and we can change the current application to work as a back end. So we add a kind of REST API interface to the current client-server application, and we use that application as a back end for a new front end that we are writing from scratch. In that way, we can completely concentrate on the front-end side, having the back-end working, because it's the old one that is consistent and we are sure. And then when the front-end is finished, we can start to do the opposite, and we start to, for example, remove some feature from the old one and start writing the new back-end, and start having the new front-end, start using some feature from the new back-end, or from the old one. I mean, it's not easy, but it can be done. And the same if you have a monolithic application and you wanted to have a kind of microservice architecture. You take the monolithics and you start cutting off some functionality and put in some containers, and you can redo with other languages. You can do whatever you want, but the idea is that baby steps, 2 weeks, deliver some value. And even if probably the intermediate system is a bit more complicated, it probably always have some advantage, because the new stuff hopefully will be better or more precise or faster or more scalable than the old one. Okay, so this is a kind of a bigger, how to split the big rewrite. But there is also another alternative, which is the decoder rejuvenation. And this is when we don't have to do such a big change, or maybe one of these changes was just, let's look inside one of the changes. And basically this is that, okay, we have a very bad Java code and we wanted to go to very good Java code. And to do this, we kind of refactoring, but in a kind of strict sense, refactoring is not the right word, because refactoring means that, as Stostrup explained in this paper, exactly keep the same behavior. Instead, we don't want to keep all the behavior. I mean, we wanted to get rid of the bugs, for example, and maybe we wanted to do some improvement in the meanwhile. So it's code rejuvenation is a better word. So the idea is it's okay to do progressive rewrite. It's okay to do code rejuvenation. It's definitely not okay to do total rewrite. And it's not okay to keep doing this kind of Dutch tape fixed when you just fix small things just to make stuff work. So, okay, if we are on this, let's see how when we do one or the other, when to rewrite and when to rejuvenate. So code rejuvenate is a kind of, so if we can keep the same code, just improve the code, it will be much safer. So if it's something that we can reuse, it's definitely a very big thing. If it's a risk for the business also, it's a very good thing to keep the risk as low as possible. And how often does have to change? Because, yeah, if it changes very, very often, we probably, I mean, we have to consider that. It can be both, but depends. One trickier part is that are we understanding the problem better now? Because sometimes, yeah, we wanted to rewrite and we do some estimation, but we're really not 100% sure what the old system does. In that case, it really is not a good idea to do a rewrite. Another question is, are we better programmers than the guy who wrote this stuff first? I mean, maybe yes, maybe this stuff was written by some external agency that was very bad for some reason or the other. But maybe not, maybe it's more or less we are the same guys, so why we think that we can do better the second time? Because usually it's not. And it can be done quickly because, yeah, you can do, the rewrite is faster, even if it's progressive, so we can do rewrite in 2-3 weeks. Yeah, probably is a good idea. If it's something that takes 6 months, I would say no, because it's never 6 months, it will be much longer. So this is a kind of a discussion that I have with some people doing after doing this talk or the kind of workshop. And some people say, yeah, our legacy code is terrible, but it's really critical for the business. And I say, hey, okay, yeah, but you know, you can rejuvenate it. You can keep improving while it's working on. And they say, yeah, we know about it. I can show you how. And I say, no, we absolutely know how to do that. It's not that. So you will start to rejuvenate. No, our code is completely impossible to change. Now, the point of this talk is that I don't think that is true. I mean, you really have to take the red pill, or no, the blue pill, and start looking. And it's really possible to change the code if you really want to, and it's not even so expensive. Okay, let's go a bit on technical side now. The talk start a bit. So a bit of typical anti-patterns on legacy code. One is called stovepipes. This is just a bit of a terminology. If you know about stovepipes, means that you have this code with monolithic application where there are some stuff that are almost, 90% identical for different flows, but completely duplicated. Another is called lava flow, because, you know, like after a volcano, then at some point someone thought that using JSON was a very smart idea, and then they say, no, now we are using YAML for configuration. Then someone say, no, we want to use this other new stuff. And there are some part of the code that are still relying on JSON, some part on YAML and stuff like that, and the code is still there, I mean, layer after layer. Then there is the classical spaghetti, where you have some bunch of code where there are all the classes that are using other classes, and it's absolutely impossible to disentangle, because everything you try to touch has a dependency on everything else. And the last but not least, the God class, when you have a nice class with like 10,000 lines of code, 20,000 lines of code that really do a lot of things, and nobody really knows why or what it was supposed to do, and you cannot really split. It's like having spaghetti altogether. And you can see, okay, we are clean code, TDD, solid principle. Yeah, let's do that. But there is a catch. I don't know how many of you know the expression catch-22. But by the way, it's a very good novel if you have some time. But the novel is about a pilot that was he didn't want to fly on the bombing airplanes, and so it was if you are crazy, you can basically got exempted to fly. But if you don't want to fly, you are not crazy by definition. So it's very hard to be proper crazy. And here in our profession, the idea is that, okay, I want to do refactor, but all the refactoring books told me, yeah, before starting the refactor, you need a unit test. And they say, yeah, but I need, to write the unit test, I need a refactor, because at the moment I cannot really refactor anything. It's a kind of a catch-22. And then this is a kind of my idea, my proposal, and it's about I call alchemical rejuvenation. And the idea is it's very simple at the end, something that I did actually more than once. And so you take your application, you seal everything with external test. Then you split your application in modules, and then you clean up just the module that you have to work with. And then once it's clean, you can write unit test to keep it clean. And then if it's needed, you can switch to other modules and do it again. I call this process alchemic rejuvenation, and the reason why it was alchemy was because I was reading this book when I was thinking these things, and this is a really good book about alchemy and nothing about programming. But the idea is that we are kind of seeing alchemy as a kind of mambo jumbo kind of trick stuff. But in the beginning, in the Middle Age, alchemy was really top-notch chemical, and the scientific foundation of alchemy was actually pretty good for their knowledge. And basically, they said that there are kind of principle inside the matter. So there is the metal principle and the ground principle, and you can mix and split. It was and there has a lot of experiment that was proving the laws. So at the end, at the beginning, was very, very science. Then when it became a kind of trickster stuff like that, the real the real good scientists start saying that alchemy has a bit of a tainted name, so let's just drop the beginning al and just call it chemistry. That sounds better, and that just to differentiate. But at the beginning, alchemy has this idea to basically to purify. And when you take a metal and you purify it completely, basically you got the gold. So how to do this? Step 0. First of all, always forgotten in here, simplify the onboarding. So you have a big project, usually the onboarding is a nightmare. So first step 0 is simplify your onboarding. You can use Vagrant, you can use Docker, you can use a script, Ansible, whatever, but you should have a solution where someone new came in the project in a few hours is able to write code in the project, because otherwise there are so many things that nobody really document how to write stuff. So just the onboarding on the project is very long, and this is really, really a problem for all the other stuff. So, second step, let's wrap it with the test. And notice that when we wanted to wrap something with test for this purpose, we want to test all in all, because we cannot really split. And we really don't know about, I mean, it's not given that the tests are something like the acceptance test, because sometimes you have just an input and output, and the input and output are really not, they are not really use case, they are not really readable, human readable, I mean. So it's something that it just proves you that the system is working, but the problem is not much, it's not a use case, they say. But it's still proving that this test can be different from the normal test, but it's very important that you have. And also notice one thing. Once you did the step 0, the onboarding, then you do this stuff. You kind of spend time, but you are not just wasting time, because you're actually creating something from the project that is useful regardless. Even if you don't do all the next steps, you still have a project that before nobody really knows how to touch. Now you have some easy setup, easy configuration, and you have some tests that you can anyway, even if you don't want to do any kind of refactoring and keep going with a terrible fix, you still have some tests that you can use. So it's actually a value for the company. It's not just. Then if you do this, you have to split in modules. And when you split a module, remember to split vertically, not horizontally. And when I mean vertically, I mean you have to split module for feature, not module for layer. So having like UI level, middle layer, and persistence layer is a very bad idea how to split in modules, because you want independent modules. And then you have your spaghetti code to work with that you can enjoy. At the end, everything is tidy and tested, so we have our nice module. And we can start with the next one. And so this is a very quick visual recipe. We start with the spaghetti plate, we put the test around, and then we start clipping and clipping this kind of. And let's do a bit of technical, some Java example. The first things is quite easy, very, very easy, but it's quite important, is get rid of the singleton, because singleton are really a nightmare when we want to do the split of the modules later. And I won't go very deep now, but the idea is that most of the singletons are either stateless or stateful. And the stateful singleton are something like sessions, cache, or stuff like that. And the kind of more difficult to remove, and what we can do, we can basically put them in a kind of service locator. So at least we reduce all the singleton to one single singleton, which is the service locator itself. All the other singletons, we have usually a lot of singleton in legacy code that we are not really, they are stateless, so they are quite, they are not very hard to remove, but having the singleton make it complicated. So we can usually just instantiate that in a different way. For example, the controller or stuff like that. Basically, we wanted to instantiate it to a higher level and then use a dependency injection instead of just having a singleton. No, this was quite simple. So the second idea is this hermetic seal. And then here are the things. Now, notice that when we did, I will speak a bit about this kind of 4 techniques. These techniques are kind of meant to be without unit test, because we are still in the phase where we cannot use a unit test. So the idea of this technique is that is very, very mechanical stuff that you do to the code without trying to improve the code or make it much, because you really wanted to keep the change at a minimum. And we only have this kind of external text anyway. But that usually are slow, so it's something that you really wanted to run once, twice in a day, and you want to be. So, how to split the code into modules? Basically, the idea is that let's introduce an interface. Let's use this interface as a kind of facade pattern, and then put everything that we want to put in another module behind the interface. And this can be done basically just using kind of IntelliJ refactoring tools. Almost, you have to think a bit before, but you really almost need not to do any kind of dirty stuff, and everything should stay reasonably compilable and working. So I have an example here, which is almost identical to a production one. I mean, I simplified, but it's quite really terrible. And so the idea is that we wanted to work on a specific module, but this module is using these two things called connection and config manager that came from, well, that's something that we don't really want to touch. And so we wanted to make sure that everything that related to connection and config manager doesn't go inside our module. So how we can cut this? So the first step one basically is define this interface, which is this data context in the top. And let's basically put in the interface the stuff that we need. And then we change our, no, you can, we try not to change our code. And we just created this interface, and we put just the stuff that we needed before. So far, so good. And then we can, well, basically, when we sometimes when we do this interface, we realize that actually we don't need so many things because we need this high-level object only because we need, for example, in this case, a config manager. We really don't need to hide all the config manager because the only thing that config manager that we use is this string risk config. This code was doing some configuration for kind of some security. And so instead of passing the whole config manager to our code, we can just say, let's just get this risk string and just use the risk string. This is just an example, but just to do something quite weird. And then we can do kind of some stuff with the other thing, with the connection. And we can hide the connection inside using basically a callback. Instead of passing the connection to our module, we can say, no, we can put a callback to this facade, and then our module, a lambda or something like that, will be called using will run using the connection. So we don't have to give the connection to our module, but just run in next time. So after these changes, basically, we change our main method with the logic, removing all the bad stuff that we don't want. We pass the new facade, and we just get the stuff with the facade, and we just get. We don't need the config manager anymore, but just we need it for the facade to give us the specific risk that we need. Also, we don't need the connection anymore. We just need the facade to run our code inside a connection context. And so at the end, we can finish the stuff. And our initial module, it just need have this execute was basically. We don't need anymore all this stuff that we don't want to, but we need this data context builder. So we need this kind of external environment. And that means that we can now test all our code mocking the external environment. So we are completely free to start unit testing. And in reality, what we can also do, we can move the stuff up, and then at the end having these modules that only have a kind of dependency at the beginning of the module, and then internally they are completely consistent. And notice that basically doing this kind of substitution is almost completely automatic, and we don't have to really risk a lot of introducing bugs. One thing that we need is kind of discipline when we do this kind of refactoring. We really have to be clear and not start doing improvement to the code while we are here. We can do the improvement once we have the unit test in place. And the last one, this Lambda archist, which is a nice thing that Java 8 gives us. The idea is that it's a very easy way to remove some code duplication without actually writing new class or inheritance, which is something that sometimes brings up some bugs. So just to give you a very simple things, we have a very two classes with very simple stuff. One is calculated the interest using the LIBOR. So from a user, get the loans from the user, then get the LIBOR rate. Then for each loan, do apply a rate that is passed in as a method, as a parameter in the method, and the LIBOR, which is kind of fixed, and then return the sum. And and then the next one basically is doing some other kind of interest using the credit check. And so we do a completely different init, and then for each loan we calculate the rate in different things. So the classes are quite similar, but they're not completely identical. We can do some refactoring, extracting using strategy pattern, but it will be a kind of risky. Something that we can do instead in a very, very simple way is it's a kind of it's not very nice at the beginning. Basically, we just introduce two lambda. Well, two functions basically as a parameter of the function of our method. One will be called in the beginning, and the other will call us on the specific. And note the nice things is that we really, because in one case we have this credit check for the initialization that we use inside the cycle. In the other case, we have just a double that is using. But with the lambda, we can use an external type. So we don't have to specify which is the type in our class. The only thing that, of course, the two lambdas have to use the same type. This A in the generics. So the actual implementation, yeah, this is the implementation of the code. So basically, we just call the two lambdas with apply. And the context, note that the context there is a type A, that we don't really know whatever is A, the only thing that we will pass to the second lambda. And this is how these two things of code will be rewritten. But yeah, the nice thing is that you can do this step by step, and then basically using the same class, introducing the lambda, starting the second class, and using the first class, and then remove completely the second class. And finally, this is the last, the fourth technique. It's called solve a coagula. And the idea is that when we have a spaghetti code, we have a lot of objects that are related to each other. And this is a bit of original code that we have an address, a client, a printer, a label, and then the printer wants the client and the label. So this is the output of the software. You write something like that. I don't have time to look at the code, but yeah, this is the original code, which is a bit of a mess. Everything is in the old one. So the idea is that, okay, you take all your code, all your function in your code, and you just put all the function in a static class. And all the function basically from a method you make everything like a static. And so of course they need a lot of parameters because they need all these parameters. But once you do this, basically all the parameters make very simple then to rewrite new classes where if you have only one parameter, for example, this getLines just work on address, so getLines definitely go on address. When you have more than one, you can decide which is the most important, or you can leave it static. But the final example is much cleaner, and all this is done with basically automatic refactoring on IntelliJ. And you can find on GitHub all the extra examples if you really want to see the code and try to do it yourself. So, to conclude, the idea is that rejuvenated decoder can be fun. At least for me it is. And this is my personal attempt to kintsugi. Of course, it's not a real gold, but it was a broken vase, and now it's kind of fixed, and it's kind of nice with this gold streak. And yeah, if there's any question, and I'm trying to collect material about this topic because I'm really interested, and yeah, I like to put some together. If there is any question, or okay, I hope to have some feedback if you enjoyed. Thank you.